Welcome to this lecture in the ongoing series of lectures in real analysis. Last time we defined the exponential function and proved that it exists. In this lecture we'll be looking at some basic properties of the exponential function. Let us quickly review what was the definition. So the definition was that the exponential function is any function f such that it is its own derivative and it takes the value 1 at 0. So it is a non-trivial thing. We showed that there is only one such function with these two properties. And we showed that it is actually given by this power series everywhere. So for each x, fx is behaving in this fashion. This we did by showing that the radius of convergence of this guy is infinite. And we introduced a notation which is that e to the x, when we write this, we mean that. So this is just a notation. Another notation that I would like to introduce is this. So this function exp from r to r, this function takes little x to e to the x. So just a jugglery of notations. Sometimes one is convenient, sometimes the other is. All right, and now let us start with the material. So the first property we want to prove is that, well, first we have a lemma and then we have a more general version of this lemma, which is the property that I want to get to. So what is the lemma? You fix some a greater than 0 and some real number b. Then we want to say this. All right, so let a greater than 0 and define a function f which takes x to 1 upon e to the a and multiplied by e to the a plus x. So note that this is legitimate because e to the a is non-zero. Since a is positive, if you look at this power series, this thing cannot be 0, right? Every term here is a non-negative term, in fact a positive term for a positive. So therefore one can consider 1 upon e to the a, and therefore this definition is legitimate. All right, great. So here is the thing. So this is for all x. This is how we define f. And since the exponential function, meaning this x going to e to the x, this is differentiable, so is f. And by chain rule, we see that f prime of x is 1 upon e to the a. This is a constant. The derivative of e at a plus x, which is again that, because the derivative of the exponential function is the exponential function. And if you just apply chain rule, you'll see that this is actually the case, which is equal to f of x. Great. What is f of 0? F of 0 is 1 upon e to the a times e to the a plus 0, which is 1 upon e to the a times e to the a, which is 1. So f is a differentiable function which satisfies f prime equals f for each x, and that f0 equals 1. Therefore f must be equal to the exponential function. Thus f of x equals e to the x for all x, giving e to the a plus b, or let me write it this way. So f of b equals e to the b, which implies 1 upon e to the a plus b equals e to the b, and this if you just cross multiply, you'll get the desired thing. So that's it. That's the proof of this lemma. Okay. And now a corollary of this lemma is the fact that this function is actually always positive. It's not just positive for positive x, it is positive everywhere. So here is the proof. So let x be some positive real number. Then by the previous lemma, e to the x minus x is equal to e to the x, e to the minus x. Because the previous lemma only required a to be positive. It did not require b to be positive. B could be any real number. So just treat this minus x as b and this as a, and you'll get that, which is equal to which is equal to, okay, so which implies e to the 0 equals e to the x e to the minus x, which implies 1 because the exponential function takes the value 1 at 0, e to the x e to the minus x, which implies 1 upon e to the x is e to the minus x, which implies e to the minus x is positive. Because this we know is positive, x is a positive real number, so this is positive, and therefore this lemma is proven. And now we can state that e to the a plus b equals e to the a times e to the b for all real numbers a and b. So how do we prove this? Well, we write down the same proof, because now we know that this is actually a non-zero number. Even if a is negative, this is a non-zero number, and hence we can carry out the same proof. So this is fine. All right. Another corollary of all this work, so this is the main property that I wanted to discuss, the first property, and a corollary of the above work is that, okay, I'll get to that corollary later. Fine. So this is our first property. So the second property is that, well, we have already seen that the image of the exponential function is contained here. It is always, the e to the x is always positive, so the image is contained here, but now we want to say more. We want to say that this is a bijection. Okay, so how do we manage this one? So clearly, this is infinite. You just look at the power series and you'll see it from that. There are other ways to do it, but just look at this expression and you'll be able to prove it. And hence, limit x going to 0, like x going to infinity, e to the minus x, which we just showed, is equal to limit x going to infinity 1 upon e to the x is 0. So we have that. And now by continuity of the exponential function, since in fact it's given by a power 3, so it's not just continuous, it is differentiable, but we'll only use continuity and the intermediate value theorem. We see that, and combined with the fact x of x is greater than 0 for all x, we deduce that this is a bijection. This is a surjection. So let me pictorially say what I'm trying to do here. I will not give the formal details because it's a simple application of the intermediate value theorem. So we see that as you go, in this direction more and more, you approach 0, and as you go in this direction more and more, you approach infinity. So the function will take all the values between 0 and infinity by the intermediate value theorem. It could do it in this way. So far we don't know if this is injective, but it will take all the values. And it will not take the value 0 because we have already proven that this is the case for all x. So that's it. That's what I'm trying to say. So this proves the bijection. This is the second property. This proves the surjection right now, not the bijection. So now to prove the bijection, we just need to also establish the injection. So for the injectivity, assume x of a equals x of b for some a and b. Some real numbers a and b. Then by Rolle's theorem, So let's say this is A and this is B, and you have the same values. So the derivative must be 0 somewhere. So thus by Rolle's theorem, x prime of C equals 0 for some C strictly between A and B, which implies x of C is 0 for some C. But that's a contradiction. This is a contradiction because we already know that this never vanishes. The image of x is contained in this guy we show in the previous slide, which is a contradiction, and therefore we are done. So I won't be writing that, but the injectivity follows basically by Rolle's theorem. So note that we are not messing around with the power series to prove all these properties. We could prove the above property by considering the product of two power series and whatnot, but that is messy. Let's just go by the root, the seed of the idea that exponential is defined via a differential equation. I just want to execute that philosophy. Great. So we have proven two properties. Now the growth rate. And before I go to the growth rate, let me just state one thing, one simple fact. Let me state that as a theorem. This thing is strictly increasing. And this is very simple because its derivative is always positive. Why? Because its derivative is itself, and this function always takes positive values. So the derivative is always positive, and therefore it is strictly increasing. That's it. And now let's prove the final property for this lecture, which is the growth rate. And what does it say? It says that this limit exists and is 0 for all n. So what is it trying to say? The above is a polynomial thing. The below is the exponential function. So this says that the exponential function grows faster than any polynomial. You can write any polynomial above. I have just written this guy. It doesn't matter because the lower order terms anyway don't contribute much compared to this guy. So this, just to keep it neat, I have written it this way. So the exponential function grows faster than any polynomial is how you should read it. And this is very simple. We can use the power series here. We have e to the x is greater than x to the n plus 1 upon n plus 1 factorial for x greater than 0. Because this is one of the terms of the power series, and all terms of the power series are non-negative for non-negative x, and therefore x to the n upon e to the x is less than n plus 1 factorial upon x. And now if you take limit x going to, this is of course non-negative, so if you by sandwich theorem or whatever you want to call it, we see that the limit x going to infinity, this is 0. So the growth rate is very fast. Great. Exponential growth rate. This is a very standard function to compare others with. Okay, great. So I guess this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.